Can you hear me? Can you hear me okay? Yeah. In the back? I have 3 microphones. I'm not sure that any of them are working. So you can hear? Okay. So I'm Mike Crommie. Thanks for coming. Today I'm going to tell you about the truth about carbon and nanoscience. Convenient or inconvenient? That's referring to carbon. And I'll just tell you the answer right now. The answer is that carbon is quite convenient for nanoscientists. We love carbon, actually. But carbon is not convenient for everyone. You might have heard that carbon in the atmosphere leads to greenhouse gases that cause global warming. And so in that case, carbon can be pretty inconvenient. But for nanoscientists, it's very convenient. And the reason why carbon is so convenient for us is because it's a fabulous building block. It's a great building block for building nanostructures. It's really versatile and it's really great. And so what I'm going to try to do in this talk is to give you some sense of why carbon is so useful and for nanoscientists and why we love it so much and some of the cool things that we can build out of it. But before I start, I'll just say a few words about nanostructures and nanoscience. I consider myself to be a nanoscientist, and what a nanoscientist does is a nanoscientist studies nanostructures. And what nanostructures are small objects whose size are on the order of a nanometer. And a nanometer is a pretty small unit of measure. It's 1/100000th of a meter, and sometimes we abbreviate it with just these letters nm. So 1 nanometer is 1 nm, and I just want to give you a sense of that size scale, what it means. And so here I've just grabbed a few things off of the web just to give you a sense of the size of different objects so you can get some sense of the scale of a nanometer. Now the smallest atom in the world, the tiniest atom is hydrogen. It just has 1 proton and 1 electron. And the width, the diameter of a hydrogen atom is 1/10 of a nanometer. All right? So 10 of these in a row is a nanometer. Now, there's something kind of interesting. When you drive your car or your parents' car or whatever, then inside the gas tank you have gasoline. And what gasoline is, it's a bunch of molecules. And one of the most important molecules in gasoline is a molecule called octane. And here it is. It's a bunch of carbon atoms hooked together with bonds with little hydrogen atoms stuck off the end. And 1 octane molecule is about a nanometer in width. So the stuff in your gas tank is a bunch of little molecules, each 1 nanometer in width. You've probably heard of, I'm sure you've heard of DNA. And DNA, the width of DNA is 2 nanometers. And every 3 base pairs is 1 nanometer. But a strand of DNA is really long, millions of nanometers long. If you take a gold crystal, like the gold in a ring that you might be wearing or in a necklace or bracelet, gold can be crystallized, and there's little crystals of gold in the gold in your necklace. And the gold atoms are 1/4 of a nanometer apart. So if I count 5 atoms in gold, 1, 2, 3, 4, 5, that's 1 nanometer. So this little chunk of gold with 5 atoms by 5 atoms is a nanometer by a nanometer. So that gives you some sense of how big a nanometer is. A flu virus is 100 nanometers across. It's bigger. And if you go into the circuit in your computer, the Intel chip, then the wires in that circuit are 1 nanometer, are 100 nanometers in width, but there's millions of them, so the chip is really big. If you look at a human hair, that's the width of a human hair. I would not call that a nanostructure. That's 50,000 nanometers across. 50,000 is the width of a human hair, so that's not a nanostructure. A dog is also not a nanostructure. The dog is about 700 million nanometers tall. Okay, so back to carbon. So why do we love carbon? Well, here is carbon. Carbon, you dig it up out of the ground, and if you take pure carbon, it comes in 2 forms. One is lumpy and rubs off on your fingers, and we call it graphite. Another kind is hard and shiny and transparent, and we call it diamond. So these are the 2 forms of pure elemental carbon. And so that's what it is. That's what it looks like. And they're pretty different. This is black and slippery and it rubs off on your fingers. This is hard and transparent and doesn't rub off on your fingers. And so the question is, why do we care about the carbon, and why is the carbon interesting to nanoscientists? Because these are not nanostructures. I mean, that's not a nanostructure. That's just a big lump of black graphite like coal. And that's not a nanostructure either. But it turns out that we can make nanostructures out of this stuff, and it's quite useful. And in order to see why the carbon is useful for building nanostructures, what you have to do is you have to shrink yourself down to the size of a single carbon atom. And you have to look at the carbon atom and think about what properties it has and why those properties are useful for nanoscientists and others. So here's a carbon atom, just a schematic drawing. A carbon atom, it has a nucleus, and it has some electrons spinning around it, and there's 6 electrons spinning around the carbon atom. There's the 2 interior electrons. We don't worry about them because they're bound tight to the atom. But it's the 4 outer electrons that we really care about. Those are the important ones that give carbon all its interesting properties. And that's sort of a typical rule for atoms. In most cases, we don't care too much. Well, we care a little bit, but the electrons really close inside of the atom don't affect things so much. It's really those outer electrons that give atoms their properties that we care about. Like, for example, why are things all the properties of the objects around us are determined by the electrons on the outer edge of atoms. Like, for example, if things are slippery or hard, shiny, transparent, opaque, that all comes about from these outer electrons. So in carbon, we have 4 outer electrons. Now, you might think of electrons as just these little particles that circle the nucleus, sort of like the way planets circle the sun. But actually, when you shrink yourself down to the size of an atom, that is not how things work. Instead, the electrons move, their behavior is determined by the rules of quantum mechanics. And what that means is that we really can't think of the electron as just sitting there at one point in space. Instead, we can only think about the probability of finding the electron at different points in space. And so we think of the electron as living in a cloud, sort of a delocalized cloud. And so here I show some clouds. These are the clouds that the electrons of carbon live in. I'm sorry these pictures are so lame. They're the best ones I could steal off the web last night at midnight. Couldn't find better ones. But nevertheless, these are accurate representations of the clouds that the electrons live in. So there's 4 electrons there's 4 outer electrons around carbon, and so they live in 4 electron clouds, and the shape of those clouds are determined by the rules of quantum mechanics. And I'm not going to get into those rules because I don't have time enough to explain it all right now, but you could take my class. I'm teaching it this semester. So here, it turns out that those 4 electrons can arrange themselves in 2 different ways. So there's 2 different ways in which those 4 electron clouds can arrange themselves in carbon. One of them is up here. We call it sp2. And here, you look there and you might think that's 5 clouds, but actually there's only 4. This lobe, see that one right there? That's 1, 2, 3, and then this vertical one is 4. That dumbbell one is 1 cloud. And each of these lobes is a cloud. So there's something special about these 4 clouds. These 3 are all in a plane. They're in a single plane. The angle between each of them is 120 degrees. So that's a circle, 120, 240, 360. They're in a plane pointing out in 3 different directions. And this 4th one is perpendicular. So this one kind of has a flat nature. Electron clouds there's sort of a flat aspect to it. These 3 at least, and then there's that one that's perpendicular. Now here, let's look at this other possible arrangement. We call that sp3. Now here there are 4 electron clouds also, but in this possible arrangement, the 4 electron clouds are pointing at the corners of a little tiny pyramid. The little pyramid has 4 corners. You can see it, 1, 2, 3, 4. So these guys, there's nothing flat about that at all. They're just sticking out in these 4 directions. They're very pointy. They're just sticking out like that. So this one is sort of a more 3-dimensional structure because it's pointing in all 3 dimensions. So what happens then is that if we take carbon in this form, where the electron clouds are arranged in this flat way, then we can link the carbon atoms like this. So this is 3 carbon atoms, and we can link them in a plane. We can make a 2-dimensional plane. They like to connect. They like to connect via these electron clouds that stick out here and bond, and so we can arrange them in a flat 2-dimensional way. Where if we take carbon where the electron clouds are sticking out in this little pyramid way, then when we connect the carbon up, it connects like a little pyramid. These electron clouds like to connect to each other. Those are chemical bonds, and so we get a 3-dimensional structure. And so that has huge implications for the world around us. That's a really big deal. This is a central idea of this. This is really the central concept that determines the properties of carbon. And here you can see it in these 2 forms of carbon. Here, for example, I show that black stuff, the graphite, that lump of coal, that black stuff. If you shrink yourself really down to the size of an atom, you'll see that the structure of that material, it comes in planes. It comes in 2-dimensional planes where the carbon atoms, these balls, are connected to each other in planes. And the reason why they're connected in planes is because all the atoms, all the electron clouds are like this, and these little guys are connected to each other. Whereas the other kind of carbon, diamond, if you shrink yourself down, you see that it's connected like this. All the carbon atoms are connected in a 3-dimensional fashion. So they're all connected to each other, and there are no 2-dimensional planes. It's what we call a 3-dimensional structure because it's connected in all 3 dimensions. And the reason for that is because all these little these electron clouds are connected in this little pyramidal fashion. And so and so now you can ask, so now that you have a little bit of a better understanding of why we have these 2 different kinds of structures, you can then start asking another question: why is this black and why is this transparent? And that's a really important question, because that also is an important aspect of carbon, that these 2 different forms of carbon have very different properties. This one is black and slippery and it rubs off on your fingers. This one is hard and shiny and transparent. So we can answer one question right off: why does this stuff slip off and make your fingers black? Well, it's because those 2-dimensional layers slide on one another and they slide off and they get stuck on your fingers. And so that answers one question, why it's slippery. And this one, the diamond, is really hard, and that's because all the atoms are linked in this really tight network, 3-dimensional network. But why is this black and why is this transparent? In order to understand that, you have to think a little bit harder. And what you have to ask yourself is, what are the electrons doing inside of the carbon? And here's a trick. First, I'll start with diamond. Look at diamond. When each one of these little clouds has an electron in it, and each one of them connects to another cloud. And so if I have 2 clouds with 2 electrons, then it's filled up. So those 2 electron clouds are filled up. And so for every 2 electron clouds, I have 2 electrons. So the electrons don't have anywhere to go. They're stuck. The structure is filled up with electrons. The electrons can't move, because wherever they might want to go, there's already another electron there. They can't move. And so if I shine light into a diamond, those electrons cannot absorb the energy of the light. If a photon comes in, the electron would love to grab that photon and jump with joy because it's got so much more energy now, because it's like it ate a candy bar. But it can't do it. It can't absorb that photon because it has nowhere to go. It can't go anywhere, so the photon just goes right through. It's transparent. Whereas here, if I look here at the graphite, then the carbon atoms are arranged in this flat way. If you start counting all of the electrons, you'll see that if you look at these vertical guys, then there's 1 electron for every 2 electron clouds. If you just count the atoms and the electrons, when I arrange the carbon in this manner, there's 1 electron for every 2 electron clouds. So an electron can jump from one carbon atom to the other because it's empty. So there's somewhere for the electron to go. So now if I shine light in, that electron can absorb the light. It can absorb the photon, and it gets all the energy from the photon, and so it can jump. It can just run It's so happy. It just runs, and it can just move through the graphite. And so what happens then is if I shine light on this guy, the electrons are absorbing the photons. It absorbs it, and the electrons are running around, but that's why it's black, because the photons don't come back to your eye. The photons go in, the electrons grab them and jump around, and so it's black. Whereas in diamond, the electrons can't move, so the photons just go right through it, and so it's transparent. And that's really important for determining the properties of carbon. So I still haven't told you why nanoscientists might like carbon. And one of the reasons we like it is because we can make little nanostructures from the carbon. And so I'll tell you about some different kinds of nanostructures that we can make from diamond and from graphite. So if we start from diamond, then what we can do is, if you consider that three-dimensional lattice of carbon that forms diamond, what we would like to do would be to break out little pieces of it. So wouldn't it be nice if we could make little tiny diamonds, we would call them diamondoids, little nanodiamonds. And to do that, in principle, we should be able to take little chunks of this lattice out. When you have a periodic lattice, you have something called the unit cell, the periodic structure that's repeating itself. And so here we have three unit cells of diamond, 1, 2, 3. So we could have little structures that are linear, or we might have them in L shape, or we might have them in triangle shapes. So in principle, there's a lot of different kinds of nanostructures that we could make out of diamond, and each of them could have different properties and be quite useful because they're so strong, and they have useful thermal properties as well. So we would like to be able to make these things and use them in devices. And if we could do that, then we would really have the strongest kind of nanostructures. So for many years, people tried to make these structures. Chemists in the laboratory tried to make them by taking chemicals and combining them in various ways. And the bottom line is they failed. They couldn't do it. It was too hard. So people have been trying to make these things for 50 years, 60 years, and they failed. They failed utterly. It was just too hard. People couldn't figure out how to do it. People aren't smart enough. But it turns out that there is a laboratory where these things can be made, and that laboratory is the bowels of the earth. Because if you go down underground, then what you find are big, huge lakes of oil. And oil, what's oil? Oil is a bunch of carbon. Where does that carbon come from? So in these big lakes of carbon under the earth, what happens is that the underground, there's a lot of pressure and there's a lot of heat. And so the oil is very hot, and all those carbon atoms are moving around, and it's the biggest chemistry set in the world, and it's a better place to do chemistry than any laboratory on Earth. So it turns out that in these big pools of oil under the ground, there are diamondoids, and the way to get them is to suck them out of the ground. And so that's what happened. These guys, Chevron, they were drilling for oil about 7 or 8 years ago. I don't know where. They won't tell anyone. It's a big secret. But they found that there was some junk that was gunking up their drill bits. And so they took their drill bits out and they took this gunky stuff and they started looking at it, and they realized that they had diamondoids, that they had these little nanodiamonds were clogging up their drill bits when they were drilling for oil. And so they found diamondoids that nobody had ever been able to make before. And so they took some of these diamondoids and they gave them to me. Because I like little things. I'm a nanoscientist. So I heard about this and I said, give me those things. And so they gave me some, and this is one of the ones that they gave me. This is a little piece of diamond. It's a little tiny diamondoid, a nanodiamond, about 1 nanometer across. And so me and my group, my students and postdocs, took this little tiny nanodiamond, and we wanted to look at it to see what its behavior is. So what we did is we stuck it into this machine that we have called a scanning tunneling microscope. And this is the world's most powerful microscope, even better than a TEM. and this microscope, the way it works is that it has a sharp little needle, a sharp little metal needle. And what you do is you bring that little metal needle really close to a metal surface, and you put a battery between the needle and the surface, and electrons tunnel from one side to the other. And by measuring that tunnel current, you can tell how far the needle is from the surface. And so if I scan that needle and measure how much current is flowing in this circuit, I measure that with an ammeter, a current meter, then I can take a picture of the surface. It's like a blind person reading Braille. You feel it, and you can feel little bumps on the surface by measuring how much tunnel current there is. And that allows us to take pictures of individual atoms and molecules. So these guys, Chevron, gave me these molecules, and so we looked at them, and this is what we saw. We put those molecules on gold. So here I have diamonds on gold. So that's like jewelry. See, this is my kind of jewelry. So I have little diamonds on gold. That's on a gold surface. You can see each little one. They're pretty small. They're about 1 or 2 nanometers across. And so I was so happy that Chevron gave me these things that we took our little needle and we started moving them around, and we did this. And I was hoping that they'd give me money. I'm serious. But they did not. They gave the guys at Stanford money. So that really pissed me off. I'm not joking. Okay, so I stopped studying diamondoids. Well, we saw some interesting things, but we soon stopped. But the diamondoids are interesting. We measured some interesting vibrational properties. But then the thing about the diamondoids is, remember I told you that the electrons in the diamond, the electrons are stuck. The electrons don't have nowhere to go because all those electron clouds are filled with electrons, so the electrons can't hop. So as a nanoscientist, I would really like to have a nanostructure where the electrons can move through it, because then I could make like a little electrical device out of it, because I need the electrons to be able to move through it. So a question is, can we make nanostructures out of the other kind of carbon, the flat kind, the kind where the electrons can move? And so in other words, can we make flat carbon nanostructures? And the answer is, of course, yes. And how do we do it? We use a pencil, because inside of a pencil, that black stuff right there, do you know what that is? Yeah, that's graphite. That's carbon. That's the flat kind of carbon. But it's all, there's a whole bunch of it, and it's all scrunched up. See, if you zoom in, you can zoom in some more, and you get, there's this flaky structure. That's the flat carbon inside of the pencil lead. And so what I would like to do is get that flat carbon, but I'd like to isolate it and just get one sheet of it, because that would be cool. That would be a cool nanostructure. Because if I look at the lead of a pencil, that is not a nanostructure. That's like a pencil lead. So what we want to do is we want to get a nanostructure. So how do we get the nanostructure out of the pencil lead? Well, what we do is we take the pencil and we draw with it. And then we look at the black stuff that's on the paper, and if you zoom in really close, what do you see? That's what you see. You see nanostructures. Because the black stuff, when you write with your pencil and you look really close, it's these little flakes, these little flat carbon nanostructures, and we call these things graphene. And somebody analyzed the stuff that comes out of a pencil and saw that it was these little flat graphene things, and he did that just 4 years ago. And this guy's probably going to get a Nobel Prize. It's like the biggest, most exciting discovery that, the stuff you write with pencils, these little flat things. This is like in my field, this is the biggest, most exciting discovery in the last 10 years. So, and all you need is a pencil. And so what we can do then is we can take that pencil and we can write with it on a silicon wafer. And so we can take a pencil and take a wafer that you can buy. You buy them, I forget how much they cost, and you take a pencil and you just write on them, and then you look really closely and you can find these little flakes of graphene. So here's some that we made in my laboratory. This is an actual photograph, and you see this little dark region right here? That little dark region is one flake of graphene. So that's basically what you get when you write with a pencil on a piece of paper. If you were to zoom in really close, you'd see lots of these little flakes. And those flakes are just one atom thick. It's the flat flakes of graphene. And so on the silicon wafer, we have silicon oxide, and then the silicon is beneath the oxide. And these are gold wires that we use to electrically contact the graphene. So we made this thing, and we took our needle, our sharp metal needle of our STM, and we brought it in really close so that we could see what it looks like what this flake of graphite, just one sheet of carbon, what does it look like when you zoom in and look at the atoms? And here I show what it looks like. This is the data. This is a zoom-in picture of that flake. So if you zoom in really small, then this is what you see. And notice the scale bar. That's 2 nanometers. 20 angstroms is 2 nanometers. And so here you can see this little pattern, these little dimples. If you zoom in on these little dimples, and what you see is this pattern, and this is actually a hexagonal pattern. Let's see, did I do? Yeah, there it is. I didn't draw that very good. That's kind of a... So there's 6 atoms around each one of these dark things, and those are the carbon atoms that are linked in that flat way with those flat... Remember those? I said that there's those 3 bonds that are in a plane. So those bonds are linked, and they create this hexagonal pattern, and we can see it. There it is. That's actual data that we measured on that flake. And you can look and you can see it's kind of bumpy. You see these rolling hills. Those rolling hills are due to the fact that the oxide on silicon, the silicon oxide, is kind of bumpy. It's not perfectly flat. It has some little rolling hills. And so that's why we see these rolling hills, because the graphene on top just covers it like a blanket. Now, if you were the size of an atom, if you could shrink yourself down onto that surface, then this is what it would look like. So this is the actual data of the graphene, and so you can see how we have this little carpet of hexagons, all connected by these carbon-carbon bonds. And I remember the day that we took this data, the microscope was kind of, there was some funky behavior in the microscope, there was some noise, and so we took a closer look and we saw something else. Okay, so as a nanoscientist, we love graphene. We love that stuff. It's great. It's cool. It's cool stuff. And one of the things that we love about it, we love that it's so flat, and we also love the fact that the electrons can move in graphene. So it's not like diamond. In diamond, the electrons are stuck. They can't move. But in graphene, the electrons can hop. And how do they hop? They hop from these perpendicular electron clouds. So one electron here can jump, boink, into there, boink. They can hop along and move. And what that means is that electrons can flow through graphene. It's conducting, like copper, like wire. It's conducting. And so that's really great, because the fact that it's conducting means that we could make devices out of it, electrical devices, like transistors that are in your computer. And we always love to make tinier and tinier devices, because that allows us to make a lot of money. That's important, but also it allows us to make smaller, more complex devices. For example, it allows us to make better video games. Faster computers make better video games. How do you get faster computers? You have to make smaller, more efficient transistors. Also, it allows us to make iPods and iPhones and cell phones, and all the stuff that you take for granted as high technology comes about from the fact that there are a bunch of scientists making little tiny devices, little tiny transistors, and we're always trying to make them smaller and faster and cheaper. And it turns out that graphene might allow us to make even smaller, better electrical devices, because we can take this flat sheet and carve it up. In principle, this is what we're trying to do right now. And if we carve it up, then we can make different shapes, like I've drawn here. This shape that I've drawn, that would make a transistor. That would be a transistor, and this distance from here to here is 1 nanometer. So that would be a nanostructure transistor that could potentially create the most smallest, fastest computer in the world. Although this has not yet been made, but this is something that we would like to do with graphene, and that's one of the reasons why we study it. But I want to mention something, which is that these electrons, when they travel through the graphene, because these little structures are so small, when you're passing electrons through really tiny structures, then you have to start thinking about quantum mechanics. Because when an electron moves, then its behavior is governed by the laws of quantum mechanics. Now, when you're talking about really large things, then you don't really see the quantum mechanics that easily. But when you shrink yourself down to the size of a nanometer, really small, then the laws of quantum mechanics start becoming very important. And so what is quantum mechanics in this context? Well, the idea here you might have heard that an electron is a particle, but it also behaves like a wave. So in quantum mechanics, particles behave like waves, and this is something you might have heard of, this particle-wave duality of, that's due to quantum mechanics. And I'll just tell you something right off the bat. An electron is not a wave. Okay? It's not a wave. An electron is a particle. It's just a little tiny particle. However, here's the deal. The probability to find that particle at different points in space, that probability behaves like a wave. Now, what is a wave? A wave is just something that goes up and down, up and down, up and down. So when I say that the probability to find an electron is a wave, what I mean is that the probability to find the electron here is high. If I move a little bit to the right, the probability to find the electron is low. It's probably not there. But if I go a little bit to the right, the probability is high. It's probably there. If I go a little bit more to the right, it's low, so it's probably not there. Probably might be there, not there, might be there. That's what I mean. That means that, so I'm saying that the probability to find the electron at different points behaves like a wave. And so if there's some other little, there's a couple of other little things to note, which is that if the electron is moving slow, then the wave is very stretched out. And so we have something that we call the wavelength, meaning the distance between the troughs in the wave. And so if an electron is going slow, then it has a very long wavelength. Whereas if the electron is going fast, then it has a very short wavelength, meaning that probability varies on a small length scale. Now, these waves are very tiny waves. The distance between these, the wavelength is really small, and that's why you don't see the quantum mechanics normally. Like if you hold a piece of wood or your shoe, you don't really see quantum mechanics in it too easily. You don't see the wave-like nature of your shoe. You know, when you look at it, it doesn't look like a wave. And the reason is because your shoe is so big. It's so much bigger. Actually, your shoe does behave like a wave, but it's just very hard for you to notice it because the wavelength is so tiny that you can't tell. But if you were to shrink yourself down to the nanometer scale, if you shrink yourself down to a length scale such that you're looking at things on the same length scale as the wavelength of the quantum mechanical wave describing the particle, then you start seeing this wave-like nature. Then you can start seeing how particles behave like waves. And so if I look at graphene, which is this flat two-dimensional sheet, then to a nanoscientist, the graphene is really just a big bucket of waves, a big bucket of electrons traveling in 2 dimensions. And so graphene is really, a sheet of graphene is just a bucket of waves. And we can actually take pictures of those waves. We can see those waves. And the way we see those waves is by using this microscope, the scanning tunneling microscope, this little needle. Because what I can do is I can take that little needle and I can bring it down and I can suck the electrons out of graphene like the way you suck milk out of a straw, or not milk, Coke. So if you're sucking Coke out of a straw, you know, just sucking it out, that's what the needle is doing here. I can just suck the electrons right out. So I can go to different points on the sheet of graphene and I can suck the electrons out. And if the probability of finding an electron is high, then I'm going to suck a lot of electrons out right at that spot. So if these electrons are in waves up and down and up and down, so then if I put my needle right where one of the waves is big, then I'm going to suck a lot of electrons out. Then if I move my needle a little bit to the right where the wave is small because of the rules of quantum mechanics, then I'm going to suck less electrons out. So if I just measure how many electrons I suck out over the surface, then I can take a picture of those quantum mechanical waves. I can take a picture of the probability waves of the electron. And so that's what we've done. So here is a picture of graphene. The graphene, this is just a topograph, a topological map. And it's kind of bumpy because the graphene is sitting on that bumpy silicon oxide. But then if I take my needle and I start sucking out the electrons, then I can start taking pictures of the electrons. And what I can do is I can take pictures of the slow electrons, we call those low energy, or I can take pictures of the fast electrons, we call those high energy. And the way I can take the pictures of the slow ones or the fast ones is by changing the battery voltage. If that voltage is small, then I'm looking at low energy electrons. If that battery has a big voltage, then I'm looking at high voltage electrons. So so what I have here is a picture of the graphene where we're taking pictures of the electrons at different energies. Here we're taking pictures of the slow electrons, and notice that you see these are the low regions, high, low, high, and you see that I have long wavelength electrons, meaning that the wiggles are on a long length scale. Now if I go to higher and higher energy, if the electrons are going faster and faster, you see that the wiggles get sharper, the wavelength gets shorter and shorter. So you might be able to tell, what we're seeing here is an interference pattern because the waves are interfering the same way that ripples on a pond interfere when you throw a rock in a pond. And so why is this useful? Well, one reason it's useful is because if you look in this picture, then this kind of imaging, what we can learn is how the electrons bounce off of different impurities in the graphene. So here are these little red X's. Those are impurities in the graphene, and what we learn from this kind of data is we learn how electrons bounce off of those impurities, and that's very important for nanoscientists to understand so that we can use that information to create different kinds of devices. This kind of information is critical for us to understand the electronic properties of graphene so that we can build better transistors out of it. Okay, so now so that's enough for graphene. Now I want to ask a different question. Is it possible to make other kinds of carbon nanostructures, other shapes, other than diamondoids or flat sheets? Can we make other structures out of graphene? And the answer is yes, we can. We can take a sheet of graphene and we can cut out a funky little shape like that, and then we can roll it up, and if we roll it up, then we get a little ball. And that's called a buckyball, sometimes known as a fullerene. And this was first done in 1985 by a guy named Rick Smalley and his coworkers. He didn't do it exactly the way I described, but that was the net result. So this molecule, this little ball of carbon, rolled up graphene, was discovered in 1985. And here you can see a better picture of it. So in this little ball, there are 60 carbon atoms, and they're arranged in a perfect soccer ball. It's exactly the same pattern as a soccer ball. And these guys got the Nobel Prize for discovering this little soccer ball. They discovered it in 1985 and they got the Nobel Prize in 1996 because it was a really important discovery. But I do want to point out that other people have studied the same structure even before these guys. For example, this guy Buckminster Fuller, you might have heard of him, he made these geodesic domes back in the 50s, and that's why we call these things Buckyballs. It's after this guy's name, Buckminster Fuller, because these Buckyballs look kind of like his geodesic domes. But I want to point out that even before Buckminster Fuller, there was another guy who was studying Buckyballs. His name was Leonardo da Vinci. He was studying Buckyballs almost 500 years ago. Is that 500? More than 500 years ago, actually. He was studying, look at this thing. This is a drawing that Leonardo da Vinci drew more than 500 years ago. That is a perfect buckyball. It's the exact same thing. So he was ahead of his time. Now, at nanoscientists, we love graphene, but we also love buckyballs. I love buckyballs. And so in my laboratory, we've spent a lot of time studying these little buckyballs. And what we can do is we can put them on surfaces. And so here, I show a surface where we put some buckyballs down. This is a silver surface. So we can take a silver crystal and we can make it really flat and smooth. The way we make it flat and smooth, I mean, if you just took a silver fork out of your cabinet or whatever, then it's not going to be smooth and flat. What we have to do is we have to clean it. We sandblast the surface and then we heat it up really hot, and then it becomes perfectly flat and smooth. And that's about almost as flat and smooth as you can make a piece of silver. And then we sprinkle these buckyballs on top. So every little bump you see here, see those little bumps? Those are individual buckyballs that we sprinkled down. And we can zoom in on a single buckyball. So here, let's zoom in on that guy right there, and that's what he looks like. That's a single buckyball sitting on a silver surface. We can take a picture of it with this STM by scanning our tip over it. But we can also look at the electrons. Remember I said that electrons behave quantum mechanically. Electrons are like waves. And even on a single molecule, the electrons are like waves. The electrons are like little waves that are just running over the surface of the molecule, interfering with themselves and creating standing wave patterns of electrons across the surface of even an individual molecule. And that's what determines the properties of molecules, are those electron wave patterns. And we can take pictures of those electron waves. We can look at the low energy electron waves as they swim across the surface of a molecule. Or we can take pictures of the high energy electron waves as they swim over the surface of the molecule of a single buckyball. And here I show some pictures that we've taken of the electron waves on the swimming over the surface of a single buckyball. These are the low energy electron waves, and they're big blobs. You see the big blobs of electron density. These are the probability waves of electrons, the quantum mechanical probability waves. And as we go to higher energy, we get different patterns. So these patterns are very important for determining the properties of the buckyballs. Okay, but what I want to do now is let's move on and let's talk about another possible structure that we can make from carbon. So I've talked about, what have I talked about? I've talked about diamonoids, I've talked about graphene, I've talked about buckyballs. So there's one more that I've left out. Do you know what it is? Diamonoids, what? One more. Cheese? Cheese is made of carbon, that's right. But we don't study that. That's not a nanostructure. Okay, but the one we do study is nanotubes. So some of you might have said nanotubes. And so what we can do is we can take a sheet of graphene and we can cut out a little piece of it and we can roll it into a tube. This was first done in 1991, and we call that little tube, this is a little tube, and the length scale is about 1 nanometer, and so the scientific term for it is nanotube, carbon nanotube. And these nanotubes actually are really interesting. And we can look at them using different kinds of microscopes. One very useful microscope for looking at the nanotubes is something called the transmission electron microscope. And this is sometimes we call it a TEM. And what the transmission electron microscope does is it shoots electrons through a nanotube, and the electrons go through it, and we detect them, and then we get a picture of the nanotube in the detector. And so here I show some pictures of nanotubes. This was taken by Alex Zettel and his students and postdocs. And the nanotubes can come in two varieties. We can either get a single nanotube, which is just a perfect one sheet of graphene rolled onto itself. And that's what you see here. This is a perfect single nanotube. We call it a single wall tube. Or we can also get nanotubes that come in concentric circles like this, one inside the other. So this is about, I don't know, how many are there? I don't know, 6 or 7 or 8 maybe, all inside of each other. Those are concentric multi-wall nanotubes. So we get these two varieties, and nanoscientists love nanotubes. We love nanotubes also. And one of the reasons we love nanotubes is because we can send electrons through them. They conduct electricity, so we can use them as little tiny wires. And so maybe one day nanotubes will be used in computers as the wires that connect the transistors. That doesn't happen today, but maybe one day that will happen. We don't know. But we can use them also as detectors, because if molecules drop on the nanotube, it will change the resistance. So even today, nanotubes are used in devices to detect molecules floating through the air. And this is what those devices look like. These are gold wires, and this is a single nanotube sitting across the gold wires. So we can pass electricity from one electrode to the other through the nanotube. Now that's all really nice. You know, we can make these electrical devices from the nanotubes. But really, one of my favorite things about nanotubes is the fact that if you take one nanotube and you put it inside another, then it forms, they can slide one on the other, and they can form bearings. So you can create rotational bearings by putting one nanotube inside of another nanotube. And they can spin, and because they spin, you can make little machines out of them, and you can make motors. And so one of the things that was made here at Berkeley, we made, it was actually done by Alex Zettel and his co-workers, but they made the smallest possible motor in the world. And here's a diagram of that motor. Here's a little, this is a single multi-wall nanotube right here. This is a little rotor, and by putting voltages on these contacts, S1, A1, S2, A2, you can make this little paddle spin. So here's the design, and here's a picture using a scanning electron microscope of the actual nanomotor. Here's the little paddle made of gold. It's just about 200 nanometers, about 300 nanometers across. And here you can see a single nanotube, and this is suspended on the single nanotube. And by putting voltages on these electrodes, we can make that thing spin. So you can make that thing spin here. You can see a little movie of it. Actually, this movie's kind of lame because it's not really spinning all the way around. I was trying to find the one where it spins all the way around last night at midnight, but I couldn't find it. But just trust me that they can make the little thing spin. Really. Although here it's just kind of doing like that. But they can make it spin. They got to actually tear the nanotube on the edges, and then it can start spinning. Okay, so that's pretty much most all of what I wanted to say. And so I'll just conclude by saying, take a hint from CO Man. Nanoscientists love carbon. And this little guy is made out of 28 carbon monoxide molecules on the surface of platinum. Thanks.
Okay, what we're going to do is